What we want to do today is first start off doing a proof that the Taylor series for e to the x centered at 0 not just converges, but converges to e to the x. How do you do that? Well, you do need the Lagrange error bound. That's a big part of it. But you also need to understand what it means to converge to something. You can prove the Taylor series converges using the ratio test without referring to e to the x at all. But we want to refer to e to the x. So here again is our first thing to do today. Use the Lagrange error bound theorem, or just error bound, to prove that the series, the Taylor series for e to the x centered at x equals 0, which can be written like this in summation notation, and of course like this without summation notation, converges to e to the x. Not just that it converges, but to e to the x for any real number x. Sounds difficult. And yeah, it's not easy if you've never done it before. Start off by letting x be an arbitrary real number. If we can show that this is true for an arbitrary real number, that will mean that it's true for all real numbers. Does that make sense? If I show it's true for an arbitrary real number x, because x is arbitrary, it doesn't matter what I pick, it'll show it's true for any real number x, or for all. Let x be an arbitrary fixed real number. But yeah, I'm not saying what it is. Could be big, could be small, could be positive, could be negative. I don't care. I can still apply the Lagrange error bound theorem to understanding the error. What was the error? E sub n of x is the error in using the nth Taylor polynomial to approximate the function. Remember, it goes in alphabetical order. It's actual value minus approximate value. F of x is the actual value. P of x, Pn of x is the approximate value. The idea here, the intuitive idea, is that no matter what x is, as long as n is large enough, these two numbers should be close together. And so their difference should be close to 0. Say that again. No matter what x is, these two numbers that I'm subtracting should be close together, as long as n is large enough, which means this thing's close to 0, because I'm subtracting two numbers that are very close together. For this example, f of x is e to the x, and p sub n of x is the nth degree Taylor polynomial, where you've got the same pattern as the Taylor series, except you need to stop when you get to x to the nth power. And do not put a plus dot dot dots after that point. Our goal is to show the error En of x goes to 0 as n goes to infinity. If I can show this goes to 0, that means these quantities are getting closer and closer together, arbitrarily close, in fact. They are approaching each other. Actually, this thing's fixed. X is fixed, so f of x is a fixed number. This thing changes as n increases. So how do you do that? Note, we will be done in reaching our goal if we show that, oh, here we go, absolute value of En of x, which is an expression that shows up in the Lagrange error bound theorem, goes to 0 as n goes to infinity. If the absolute value of a number goes to 0, then the number itself is going to 0. Because if the number itself was not going to 0, like if it was going to negative 0.5, then its absolute value would not go to 0. So let's now write down what the Lagrange error bound says. The Lagrange error bound gives you an inequality that is bounding the absolute value of En of x. And remember, it looked like this. It's less than or equal to capital M over n plus 1 factorial times the absolute value of x minus a to the n plus 1 power. What is a? A is where you're centering the Taylor series and the Taylor polynomials. In almost every example we've done, a has been 0. And yes, that's the case in this example as well. 0 for this example. Because that's the Taylor polynomial centered at 0. I can derive this polynomial by taking derivatives of f of x and plugging in 0. If I took derivatives of f of x and plugged in some other number like 2, I'd be trying to find coefficients for the Taylor series and Taylor polynomial centered at 2. And I'd have powers of x minus 2, not plain powers of x. That's why this is centered at a equals 0, and that's why that's 0. I shouldn't stop there. I should describe how to find m, where m turns out to be an upper bound of the n plus first derivative of f over the entire interval between a and x. Whether x is positive or negative, it doesn't matter. The absolute value of the n plus first derivative, that notation means derivative, right? If n is 10, then that's the 11th derivative. If n is 20, it's the 21st derivative. I'm going to use a different variable name here. I'm going to call it t. Why not x? Because at the start of the proof, I already assumed x was fixed. I want this inequality that I'm about to write down to be true for all t, where t is just a letter representing an arbitrary number between a and x. This is true for all t, all numbers t between x equals a, which is 0 in our case. Oops, I shouldn't use an x there. Between a equals 0 in our case and x. X at the start of the proof was an arbitrary fixed real number. If x is positive, this would be the interval from 0 to x. If x is negative, it would actually be the interval from x to 0. So this looks pretty difficult. How in the world is this going to be helpful for us? Take a breath. Say to yourself, okay, I guess I need to figure out what m is. And actually, there's not one choice for m that works. There are actually infinitely many choices you can make for m. We just need to find one choice that works. But how? Well, you know, e to the t is a very special function. I'm still using t now because, again, I'm thinking of x as fixed. All of its derivatives are the same, e to the t. And in particular, its n plus first derivative for an arbitrary positive integer n is also e to the t. This is true for all n and for all t. E to the t is a nice function because of this property. Still not out of the woods. Still may not be clear how to find m. Draw a picture. I'm going to graph the function e to the t. I'm going to label the horizontal axis with t. The graph of e to the t is your standard exponential growth function. This is f of t equals e to the t. What could I use for m if x happens to be negative? What if x is over here? There's a very simple number I could use for m, and here's a big hint of where it is. What number is that on the y-axis? It's either 0, which is 1. If x is negative, I could use m equal to 1. Because if x is negative, e to the x is less than 1. However, that's a problem if x happens to be positive. If x is over here instead, I'm going to label this x as well, but don't let that confuse you. I'm essentially just thinking about a couple examples at once. It's different colors. So that's a red x, that's a purple x. And so they're not the same x, okay? E to the x when x is negative, and when x is right there, is the second coordinate of this point. That would be e to the x for the red x. Less than 1. E to the x when x is positive is going to be the second coordinate of that point. That's not less than 1. It's bigger than 1. I can't use m equals 1. I'd have to use something bigger. But wait a minute, I don't know what x is. How can I choose something bigger? You can use e to the x itself because x is fixed. So e to the x is a constant. You can take m to be e to the x. Is there a way I can combine these cases into one case? I said if x is negative, I could take m to be 1. And if x is positive, I could take m to be e to the x. But is there a way to kind of like just avoid cases? Yeah. In general, you could let m be e to the absolute value of x. If x is positive, e to the absolute value of x is e to the x. That's like the purple case. If x is negative, the red case, e to the absolute value of x would be still e to a positive number. And would be bigger than 1. And in fact, if these 2 points were the same distance to the origin, I could use the same value up here as a bound for this value. That'll work no matter what x is. Then this n plus first derivative, which is e to the t, which, by the way, I can get rid of the absolute value signs with because e to the t is always positive, is less than or equal to e to the x, e to the absolute value of x, for all t between 0 and x. Question? Well, I just wanted to do it that way to simplify it to one case effectively. It works. It works. I could use, there's other choices I could make. Hang on, there's other choices I could make here. This is not a unique choice. But it works certainly, it's certainly the best choice that works when x is positive. And it also happens to work when x is negative. Yeah, e to the x is greater than or equal to this, to e to the x, to itself, the second coordinate of that point. But when t is between 0 and x, when x is negative, t is negative, and the output at that value of t is higher than e to the x, so it doesn't work. So this has got to be what you use in general. So what have I gotten out of this? I've gotten that the absolute value of the error, going back up here, is less than or equal to m, which is e to the absolute value of x, over, looking up here again, n plus 1 factorial, times absolute value of x to the n plus 1 power. Remember, x is fixed. So the question is, does this, for any fixed x, go to 0 as n goes to infinity? The answer is yes. The book gives you a little bit more rigorous argument than I'm going to give. And well, mine's not really an argument. Mine's just some experimentation with Mathematica. It does go to 0 as n gets larger and larger, in spite of the fact that both that quantity grows fast as n grows, and this quantity grows fast as n grows. But it's like the factorial wins out. Factorials actually grow faster than exponential functions. The factorial wins out enough to make this go to 0, no matter what x is. Now, the bigger x is, the slower it will go to 0. But eventually, even for very large values of x, it'll go to 0. Here's some Mathematica to help you believe it. I'm going to make it manipulate, which makes animations. We may use it to make animated graphs before, but this time I'm actually going to animate some numerical values. I'm going to plug in this expression. And I'm going to allow myself to change x and n. So it's e to the absolute value of x in the top here, capital E to the abs of x, divided by n plus 1 factorial, times the absolute value of x to the n power, or excuse me, n plus 1 power. Let's start x at a value of 0.1, for example. Maybe we should try negative values too. Okay, let's just focus on positive values. 0.1 and go up to as high as, say, 10. And let's let n start at a value of 0 and go up to, say, as high as we might need, which I'm just going to guess maybe 50. Although I need to put an extra comma 1 here because n is going to take discrete jumps. 0, then 1, then 2, then 3, etc. This is code that will show the values of this expression. And what I want to see is that those values go to 0 as n gets larger, no matter what x is. So here's the case when x is 0.1 and n is 0. Increase n, yeah, that goes to 0 pretty rapidly. But what if we make x bigger? Like, how about close to 1? That got bigger. But it still gets small as n gets bigger. Okay, try yet a bigger x. How about close to 4? This is getting to be a pretty big number. But if I increase n, it will eventually get smaller, though it could get bigger at first. Watch it here. I'm going to increase n from 0 to 1, and it got bigger. Then from 1 to 2, it got bigger. Oh, now it's getting smaller though. And still goes to 0. All right, the biggest value of x I'm allowing myself to try here is x equals 10, it looks like. There's the value when x is 10 and n is 0. If I make n bigger, it gets bigger, continuing to get bigger. We're up about 55 million there. But if n is large enough, it starts coming back down. Now it's coming back down. And eventually it becomes very small when n is really large. So that's no proof, right? That's just computer experimentation. But I hope it helps you believe it. This goes to 0 as n goes to infinity. This entire thing here. Which means, therefore, the absolute value of the n of x goes to 0 as n goes to infinity, and en of x itself goes to 0 as n goes to infinity. And that does the proof. Okay, so it's not just that the series converges, which could be confirmed with the ratio test. It's that converges to e to the x. Though this does still beg a question. We're using the Lagrange error bound, but how do you know the Lagrange error bound is true? We didn't address that, and we're not going to. Though if you desire to, it's in the reading near the end of section 10.4. It's a section labeled deriving the Lagrange error bound. It's very technical, involving a bunch of inequalities and integrals. Goes on to the next page, continues looking pretty technical. Not something that most people are interested in. If you find yourself to be interested in it, that means you may be a pure mathematician without knowing it. Okay. Maybe you're not interested, but you just have to know for sure that it's true. And so you force yourself to go through it. That happens too. But I imagine probably most of you will not. Okay.